Adventure is the third and final presentation in a series documenting the development of the Harbor Oil Spill Removal Recovery Systems program. Conducted by the Civil Engineering Laboratory, the program was under the sponsorship of the Naval Facilities Engineering Command. Phase 1 of the program, completed in fiscal year 1973, identified the best commercially available hardware and assembled the components into two different recovery systems, one for confined harbor areas and one for open harbor areas. The subsystems investigated in Phase 1 included containment booms, oil skimmers, storage and transfer equipment, and oil-water separators. These tests have been covered in an earlier film. Phase 2, which was completed in fiscal year 1976, was partially documented in another film. The remaining portion of Phase 2, which was a harbor evaluation of utility equipment, plus all of Phase 3 field work, will be covered in this film. The objectives of Phase 2 were to develop standard performance testing procedures for booms and skimmers, to improve equipment and procedures, and to evaluate utility equipment in a harbor. During Phase 2, several recommendations were made for improving the utility equipment. Standard test procedures were used to evaluate 2 skimmers and 2 booms. The concluding portion of the Phase 2 tests was the evaluation of the oil spill utility equipment. Here, the flat-top boat used in these tests is deployed over a ramp. This is the recommended procedure to avoid damage to the boat. The ramp is capable of being raised or lowered to the point where the water reaches the waterline of the boat at the stern, and the engines can be started. Deployment of the 2 20-foot utility boats used in the tests is accomplished by a crane. A power assistance unit for deploying and retrieving booms was developed for CEL under contract and modified by laboratory personnel to overcome some deficiencies. Here it is used to deploy a 300-foot section of Kepner 48-inch boom and 2 300-foot sections of Bennett Class 3 boom. A utility boat tows the boom away from the pier and into the harbor, with the tow lines attached to a Sampson post on the boat. The Sampson post is a CEL modification for greater stability and maneuverability. The utility boats are equipped with 85 horsepower engines with 14-inch diameter, 15-inch pitch propellers. The time and effort involved in manually retrieving the boom from the water and faking it on the pier are well demonstrated as this portion of the test concludes. It is apparent that boom retrieval by mechanical means, whenever possible, would be considerably faster and less exhausting for the crew. Now the booms will be loaded on the deck of the 28-foot flat-top boat. 3 kinds of deployment and retrieval procedures for booms were evaluated in these tests. From the pier into the water, from the pier onto the flat-top boat, from the flat-top boat into the water, and the reverse of these procedures. 900 feet of mixed boom were loaded on the deck of the tri-hulled flat-top and faked athwartship on the deck. This is the total boom transport capacity of the boat. The utility boat was tested in a towing mode, in this case, pulling the loaded flat top. The stern tow was conducted at maximum throttle. In this test, the load on the flat top boat weighed 4,350 pounds, including the boom and the crewman. The maximum speed of the utility boat in this mode was found to be 6 6/10 knots. The maneuverability of the utility boat while towing the flat-top boat was excellent, and both boats handled well. The flat-top boat was also tested under its own power using the 275 horsepower high-performance outboard motors. A maximum speed of approximately 16 knots was achieved with the boat fully loaded. The turning radius with the engines at idling speed was found to be about 30 feet. A test was conducted to determine the time required to deploy 900 feet of boom from the flat-top boat using the utility boat. The sea condition was one of no wind and no waves, and the boom in this case was stowed athwartship. It was felt that this method of faking the boom on the deck made deployment less difficult and cumbersome. A crew of 6 men was required for this operation, 2 men in the utility boat and 4 men on the flat-top boat. The total time required to deploy the 900-foot boom in this manner was just under 9 minutes. As the evaluation continues, the utility boats tow the boom into position to encircle a ship berthed at the pier. The boom ends should be secured to bulkhead attachments on the pier. Here, the boom is deployed to simulate oil containment around a ship between the pier on one side and the boom on the other side. Each of the 3 containment boom mooring systems evaluated consisted of an anchor, a mooring buoy, and a crown buoy. They were designed for nominal holding forces of 2,000, 5,000, and 10,000 pounds. The buoys were designed to have an additional 100% reserve buoyancy to prevent submergence of the boom. The medium and large systems were deployed from the flat-top boat because of their size and weight. To retrieve the mooring system, the crown line of the crown buoy is picked up, the line is fastened to a cleat, and the boat is slowly backed away from the anchor in a direction opposite to that used during deployment. The anchor is pulled loose, then the shackle of the boom connector is disengaged, and the boom is lowered back into the water. 7 crewmen were required to retrieve the boom. 4 to haul it out of the water and fake and stack it on the deck, and 3 to handle the utility boat and the flat-top boat. 4 of the crewmen worked in teams of 2, alternately pulling the boom over the roller and stowing it on the deck. The shortest time for recovering the 900-foot boom was 18 minutes. The task was noticeably tiring for the crew. When fully loaded, the flat-top boat heads for the pier to discharge the boom. The retrieval of the boom from the flat-top boat to the pier was carried out under calm conditions. 2 men were required on the boat to bring the boom toward the power assistance unit and keep it in line. The use of a forklift to pull the boom over the tires of the power assistance unit reduced the time and effort as compared to retrieving the boom manually. In addition to its other functions, the flat-top boat may also be used to tow the storage bag carrying the oil-water mixture from the spill site to the pier for storage. Here, the 30-foot-long container is being towed from the stern of the flat-top boat. The ease with which boom sections can be connected or disconnected was demonstrated. The universal connector shown here can be disconnected by 2 men in less than 15 seconds. Reconnection takes the same amount of time. A 3rd person is required to control the boat. A 4th crew member is present here, but does not participate. The utility boat is recovered in the same manner as it was launched, using a crane. The retrieval was completed in 3 minutes and required 4 men. The procedure for retrieval of the flat-top boat is the reverse of the deployment procedure. The boat is maneuvered under its own power to a position of alignment with the trailer on the ramp, then run up the ramp as far as it can go using its own propellers. A winch line is then attached, and the boat is pulled out of the water by the truck. Several tests incidental to the main operation were conducted during Phase 2. A sorbent distribution system developed by the Naval Weapons Support Activity had previously been found to perform satisfactorily in all respects except that it generated unacceptable amounts of dust under wind conditions. 3 modifications to reduce this hazard were designed and tested using simulated conditions in the laboratory. Here, a test using a cover to reduce the top opening of the bin proves to be unsuccessful. In the second test, a tapered metal hopper was used. This method showed no noticeable improvement. In the third test, a polyester fabric boot was attached to the bin opening. Visual observations and motion picture records indicated a very substantial improvement in the dust level with this method. The holding capacities of the mooring system anchors for this 5,000-pound mooring system and the larger and smaller systems were tested on a sandy beach. Each anchor was slowly dragged by a bulldozer, and the maximum pull exerted on it was measured by a dynamometer. The objectives of Phase 3 were to conduct cost and system effectiveness studies of oil spill cleanup operations and to evaluate new equipment. At the Navy Public Works Center, Norfolk, Virginia, effluent from a defective oil-water separator made its way into the harbor through a storm drain and afforded an opportunity to witness oil spill removal equipment in operation. The spill was contained by a Bennett boom. A JBF DIP 3001 skimmer demonstrates its versatility as it maneuvers in the confined area between ship and dock. The DIP 3001, selected during the Phase 1 tests as most efficient for the open harbor area system, is an inverted belt-type skimmer. Skimmers of this type operate on the principle of collecting the oil under the surface of the water. Buoyant forces cause the oil to surface in a collection well, forcing water out the bottom. Harbor debris that might damage the skimmer or enter the collection well is picked up by a crew member. Sorbent chips, which had been manually distributed to soak up the oil, are retrieved by crew members in a punt. These operations effectively cleaned up the spilled oil. The final series of the Phase 3 tests was conducted at the Environmental Protection Agency's OMSET test facility. The tank is shown here. Waves are generated by two flaps which oscillate back and forth. Choppy waves, typical of those found in harbors, are generated by the flaps oscillating 180 degrees out of phase with each other. Oil is spread on the water for a stationary test of the Comara mini skimmer, which recovers oil on rotating oleophilic discs. It is surrounded by a section of boom with an 18-foot radius. A diesel engine supplies power to the skimmer. For 19 of the 21 tests conducted in this configuration, using number 2 fuel oil, approximately 26 gallons of oil were spread on the water surface by a splash plate. If the oil had spread uniformly within the boom, the thickness would have been approximately 1 millimeter. During each test, the recovered oil-water mixture was pumped continuously into translucent measuring containers. It was then thoroughly mixed with an electric stirrer and samples were taken. These samples were centrifuged to determine the oil content, from which the oil collection rate and the collection efficiency, that is, the percentage of water in the collected oil-water mixture, were computed. During one series of tests with the Comara skimmer in the stationary mode, a high wind was blowing, with gusts up to nearly 20 knots. It was found that the wind drove the oil into the skimmer much more effectively than hosing. For this group of tests, the average oil collection rate was 2 4/10 gallons per minute, more than twice the rate for winds with gusts up to about 7 knots. From this, it was concluded that high winds improved the collection rate more than hosing with a single hose. For tests in the advancing mode, the Comara skimmer was placed in the apex region of a boom in a catenary configuration. The boom was connected to the skimmer at its maximum diameter. The boom-skimmer combination was then towed by the OMSET towing bridge. During the course of each run in this mode, the recovered oil-water mixture was pumped into containers located on the trailing truss of the towing bridge. To make the most efficient use of the Comara skimmer, a section of boom was placed behind it to contain the bypassed oil. The toroidal arrangement of the skimmer discs makes it possible to collect oil along the complete circumference of the skimmer. As shown in this underwater view, oil is escaping beneath the skimmer. Oil can be driven underneath by the skimmer blades or by higher tow speeds. The effect of waves was found to significantly lower the oil collection rate and the collection efficiency of the skimmer. The collection efficiency decreased because waves tend to throw proportionately more water than oil into the collection well. For the first set of stationary tests on the Lockheed Clean Sweep skimmer, it was placed within the apex of a catenary-shaped boom configuration. The Clean Sweep also recovers oil on rotating oleophilic discs. Arranged in a straight line, 10 discs pick up the oil. As the discs pass between two wipers, the oil adhering to them flows into a collection trough from which it is pumped. In this test, the front of the skimmer faces the apex region of the boom, and the oil is hosed around and probably under the skimmer to form a pool in front of it. For tests in the advancing mode, the Clean Sweep was towed with the front of the skimmer facing the oncoming oil slick. Again, underwater photography shows oil escaping beneath the skimmer. In the presence of nominal waves, 1/2 foot in height, the oil collection rate of the Clean Sweep dropped by a factor of approximately 2. Because the discs are protected by cover plates, the oil thrown against the skimmer by the waves could not easily contact the discs. The Seahawk skimmer is essentially a weir with an attached storage bag. Oil must pass over a ramp into a collection well from which it is pumped. In stationary tests of this device, 2 booms were attached to the front of the skimmer, and 2 fire hoses were used to drive the oil over the ramp into the collection well. For tests in the advancing mode, the Seahawk skimmer was towed in the same configuration used for the stationary mode. For the test without waves, it was found that the oil failed to go over the ramp into the collection well when the lip of the ramp was at or above water level. This was corrected by adjusting the ballast. In the presence of waves, oil did go over the ramp when the lip was set at water level. On the basis of these tests and tests conducted earlier during Phase 2, the JBF DIP 1001 skimmer was found to have the highest oil collection rate in the stationary mode of the medium-sized skimmers tested. The collection rate was 11 gallons per minute. In the advancing mode, the Comara had the highest oil collection rate, 5 7/10 gallons per minute, at a tow speed of 1/2 knot in an oil slick 2 4/10 millimeters thick. A new type of containment boom was also tested at the Omset facility. This was the Whittaker Expandy boom, an air inflatable model designed in 82-foot sections. The boom is packed in a protective fabric cover and will float even when packed. When the protective cover is removed, the floating sections automatically expand as air is drawn in through valves. Tests on the Whittaker boom were conducted using one 82-foot section in a catenary configuration. Testing conditions included no waves, following waves, and head seas. With no waves, the boom started to lose oil at a tow speed of approximately 9/10 of a knot. In the presence of waves, it began to lose oil at less than 1/2 knot. The oil loss rate in the presence of waves was lower than that of the Bennett Class 3 boom tested during Phase 2. The Whittaker Expandy boom is considered to be a superior oil containment boom for several reasons. It is easy to deploy. Just throwing it in the water is adequate. The stowing volume required is an order of magnitude less than the volume required for other booms. 300 feet of the boom can be stored in the trunk of an automobile. And finally, it exhibited an excellent articulation in waves, which was responsible for its superior oil containment performance. The Harbor Oil Spill Removal Recovery Program has now been completed. During the course of this program, the best available commercial equipment was identified and evaluated, and recommendations were made for improvements. In addition, analytical studies were conducted to determine cost-effective procedures for cleaning up harbor oil spills. All the information gathered has been submitted to the Naval Facilities Engineering Command in support of their task to provide naval activities with the best equipment to carry out the Navy's goal of minimizing pollution due to harbor oil spills.